I would like to welcome you all to the Senior Capstone Project presentations from the School of Engineering and Applied Sciences. This morning we're covering the electrical and computer engineering. My name is Dr. Esther Shosanya, Professor and Chair of Electrical Engineering. Senior Capstone projects represent the culmination of the educational experience, integrating the classroom with real-world problems. The students handle open-ended engineering problems whose solutions require a synthesis of engineering knowledge, analysis, creativity, market needs, safety, and aesthetics. Projects are carried out by students and supervised by instructors and industry mentors. Today we have 5 presenters. Our first presenter will be Jonathan Prado Valdivia on 2.45 gigahertz Wi-Fi RF energy harvesting for low power devices. So Jonathan, I'm going to stop sharing screen and you can start your presentation.
Good morning, everybody. Let me pull this up for you guys. Can you guys see it?
Yes.
Okay. Hi, everybody. My name is Jonathan Prado Valdivia. I am a senior at Electrical Engineering and Computer Engineering Department. My project is going to be 2.45 gigahertz Wi-Fi energy harvesting for low power devices. I would like to start out the presentation with a quote. As the saying goes, the Stone Age did not end because we ran out of stones. We transitioned to better solutions. The same opportunity lies before us with energy efficient and clean energy. This was said by Stephen Chu, former United States Secretary of Energy. So my mission is to utilize the established Wi-Fi infrastructure to harvest wireless energy in order to charge a 5,000 milliamp per hour portable battery bank. The materials I use for this project is a 14 dBi receiving 2.45 gigahertz antenna, a 5,000 milliamp portable battery bank, a breadboard, a Wi-Fi source, in this case it will be a router, embed microcontroller, a P221XX CSR evaluation board, and miscellaneous equipment like wires and connectors. The result is going to be by harvesting the Wi-Fi waves. I hope that to maximize the use of the existing technology as a clean source of energy that will be able to provide energy for low power devices. What is Wi-Fi? As we all know, Wi-Fi is very popular nowadays. We all use it to communicate with each other, and we're using it right now to talk to each other as of now. Wi-Fi is a wireless radio frequency signal that allows wireless devices to connect to the internet. The connectivity occurs through a wireless router and allows access to the internet. The Wi-Fi signal emits a 2.45 gigahertz radio frequency signal that can be picked up by wireless devices. A 5.0 gigahertz frequency signal is also used for lower latency between wireless devices and the signal source. At a higher frequency, the distance the signal travels is shorter. So for this experiment, I did use the 2.45 gigahertz because it is the most common wave and it travels the furthest from the two waves that were currently being used. What is RF harvesting? RF harvesting is the process of using RF waves, radio frequency waves, to power or charge electronic wirelessly. The process can be used to trickle charge a battery or power battery-free devices upon collecting enough power through a capacitor. The process is used an antenna that can capture a specific range of RF waves and convert them from AC to DC voltage and charge small power electronics. As the diagram shows below, the transmitting antenna sends the signal, the receiving antenna receives the signal. It's an impedance matching, and then it goes into a voltage multiplier, and then the capacitor ends up charging. When the capacitor reaches a specific threshold voltage, the capacitor is discharged.
Good box.
And
You turned it.
and that reaches the source of battery or device.
The senior project day is virtual. They're right now talking about.
Can you mute yourself, Hans?
The importance of this project. In the current world of climate change, multiple countries are putting a great emphasis on renewable energy sources. Solar, wind, and biofuel are the leading of the pack, but yet to achieve the efficiency needed to replace fossil fuels. While research continues into these power sources, pollution accelerates and destroys the planet. Utilizing RF harvesting at large sources of pollution, disposable batteries can be discontinued, therefore decreasing the waste in the world that we have today. So as we know, multiple devices use discardable batteries. Unfortunately, these batteries don't always get disposed the correct way, and a lot of end up in the wasteland. And at the end of the day, they end up seeping through our waterways and polluting our environment. My hope is to be able to use this RF harvesting to be able to replace disposable batteries in small powered electronics that can be powered through this method itself, and be able to reduce the pollution that is created in the world today. My objectives. During the project, I tried to determine the type of antenna needed to access these required frequencies. Each antenna has a specific frequency range that it can capture. So I had to find an antenna that captures about 2.45 gigahertz waves. Then do some research on acquiring a RF harvester that can capture these specific types of waves. There's a bunch of different out there, from low frequency from 900 megahertz up to about 5 gigahertz for harvesters. So I had to find a specific harvester that we would actually capture the specific waves. Then I build a prototype and do real world testing. Starting out with different antennas, going down from even 4 dBi antennas for receiving, and I ended up sufficing at a 14 dBi antenna for longer range. I take the prototype and improve the design. That's what I did with the increasing the powerful antenna. And finally, I build the design and real world testing here at home and at the engineering lab at school as well. So this is the RF harvester. So you can see from the picture below, the bottom input for the antenna is going to be the input needed for the 2.45 gigahertz. That's going to be the Wi-Fi receiver antenna. Then we see below, there's frequency ports. When selecting that specific antenna at the bottom, you would have to do a jumper to connect that circuit, knowing that you're going to be using that specific wave. From there, we have 3 different options for threshold voltage, 0.7, 0.9, and 1.2 volts. For my final experiment, I went with the 1.2 volts. On top, you can see the output voltage. This will select the output desired at the end of the charging of the capacitor. This voltage is acquired through voltage multiplier that is done through the module inside the circuit board itself here. Then we see the output port selection. This board itself shows 3 different types of outputs. The LED, which is used to just test that the breadboard, that the harvester does work when the threshold voltage is reached and the capacitor is discharged. LED in the middle of the board will turn on just to verify that the board is currently working. To be able to use it as an actual voltage source, we switched it to VCC, which just allows us to connect different devices to the board itself for it to charge or power. And finally, we have the capacitor. The board itself has 2 capacitors available to it, 22 microfarads, 2200 microfarads, and 50 millifarads. The 50 millifarads is the one that I use for my experiment because it is a supercapacitor, and when charged, it does charge at a constant rate, and when it's charging, it does keep a steady decrease until it reaches that voltage that it will stop. So it was the most efficient out of the two that I had. And at the bottom, we can see low battery, low impedance output port. So this board does allow you to have two different output ports for the charging a battery. I chose a low impedance voltage port because we are charging a lithium battery. It does not have that much resistance between it. It does allow, this port allows itself to provide some resistance for the battery not to discharge into the board itself, and only allows the voltage to be emitted. Here are the components of the board itself that are being made up. We can see from the top, we see antenna module. So this module is where the J6 is where the antenna will be hooked up. The module in the middle, the PCC1110, is going to be an AC to DC rectifier that will release the DC voltage. From there, we can see the single band selection module. This is the port where you select the 2.45 gigahertz specific wave, and it will go through the system circuitry itself and go through the capacitor. Next, we have the capacitor selection module on the left side. This is the selection of the capacitors that we have, the 50 millifarads and the 2200 microfarads. Like I said earlier, I did select the 50 millifarads as my capacitor itself. Next, we have the threshold voltage selection module. This will select the threshold voltage that you do want to select. I only put the 1.2 volt because that's the one that I selected for this specific experiment. Then we have the output selection module, that where you'll choose the VCC in this scenario underneath the measure 1, and that will release the voltage into different output sources on the board itself. And then we have the output voltage selection, where we have the standard 3.2 volt, and then 4.1 volt and 4.2 volt. Again, for this one, I did choose the 4.2 volt as the output for the board. And then we have the RF harvester module itself. And this module itself will be a voltage multiplier that will take the voltage that was released from the antenna and the capacitor and use voltage multiplier depending on the output voltage selected previously, and will emit that specific voltage. And finally, we have the impedance selection for battery charging. Here we'll go, I did do the low impedance, which will be all the way on the right over here. That will go through that through this module in itself and charge the battery from that specific port. Next, since we are during COVID, unfortunately, the lab is not as accessible as to us as it used to be. So one of the biggest things about this project is I needed to test the voltage, needed to figure out where how much voltage I'm getting after each experiment. So what I did is I created a digital voltmeter through the mbed microcontroller. So this would be my code that I made. Here we will start with, I selected 2 terminals as an analog in. So 1 terminal for the capacitor voltage and 1 terminal for the voltage out. In the main code, we'll be selecting, we'll be able to print out voltmeter as the title of the voltmeter, digital voltmeter, and at the same time be able to read 2 voltages instead of just 1 at a time. The 2 voltages will be presented as capacitor voltage and output voltage, and it will be seen later in the video presentation. So this was the setup of the equipment itself in one experiment. So the closer you are to the 2 antennas, the more frequency. I'm sorry, the lower the time it is for the capacitor to charge itself. So since I didn't have that much space on this desk, I was able to show you guys how it will be all together at a good distance. Here we see the RF harvester, the receiving antenna, the Wi-Fi source, the digital voltmeter on the breadboard itself, the battery pack, and the port that connects from USB-A from the breadboard to USB-C to the battery pack. So the results that I did get from this experiment, I was able to use the RF harvester for an output voltage of 4.2 volts and a 20 milliamp current that harvest using the threshold voltage of 1.2 and a capacitor of 50 millifarads at 5 feet from the signal source. I have been able to get harvest waves at about 10 feet, but the downside from that has been that it takes a lot longer for the capacitor itself to charge. So I settled with the 5-foot distance where it's still pretty far away, but I still get enough signal harvesting that is actually useful for charging the battery itself. The voltage will be trickled down and charge the battery, and when fully charged, it can be used to power small electronic devices like cell phones and wearable devices. Another thing that could be used, this is more of a proof of concept. This itself, the module for the harvesting, could be installed into small powered electronics that constantly receive RF signals like cell phones and like smart watches and so on. These are the sources. I did base this project based on a previous project done by the engineering students here at UDC. Instead of using Wi-Fi waves, they used 226 millihertz waves to power a weather sensors to send signals to a different location. But I based off mine as a conservation, sustainability kind of project. Another big source is PowerCast, which is the manufacturer of the harvester itself, and they're the ones that provide the schematics to the diagrams and so on. And if I have time, am I able to show the video, Dr. O? Sorry, I can't hear you. You're muted.
How many minutes for your video?
It's 5 minutes.
Yeah, go ahead, and then we open up for questions and answers.
Okay.
So this is my name is Jonathan. Senior in my project is RF harvester. I'm using 2.45 gigahertz wave Wi-Fi waves to be able to harness the power of the harvester here and transmit it and trickle charge this battery pack here. So how this works is I have a router right here with 2 small antennas for directional charging, and then a broader antenna with 15 dBi range on it that shoots it to this 10 dBi antenna that receives it. From here, I have a threshold voltage of 3 options between 0.71, 0.95, and 1.2 volts. Depending on that, it charges 2 different capacitors of my choosing. When the capacitor reaches a specific threshold voltage I assigned it, it releases the voltage. I have an option of 3 voltages, 3.2 volts, 4 volts, and 4.2 volts. So you can see here, as we can see it right now, it is set up as a 0.7 threshold voltage. So this measurement right here is detecting the capacitor's voltage. So when it reaches 7 voltage, it'll go about 7.3 because of the difference of measurement. It will discharge, send the voltage out to the 2 prongs over here, which will then send electricity to this USB port that I have connected for voltage and ground, and then send the energy to this battery right here, and it'll trickle charge the battery. My biggest problem that I've had in this project is trying to get the distance between where the signal is coming from and where the harvester is. Right now, this is the furthest I've gotten it. I can go a little further away, but the problem would be it'll take longer for it to reach the desired voltage. Right now, the way I'm thinking about improving it is that I have ordered another antenna, which is a 14 dBi antenna that will be able to receive the higher signal from this antenna as well, and hopefully increase the distance up to 10 to 15 feet. This is something that will be more efficient in a more practical kind of way.
So this is the current updated project. Here we have the harvester connected to the 14 dBi antenna, receiving antenna. And this is receiving signals from this 15 dBi emitting antenna, getting powered by this router. There's no Ethernet connected to it. It's just strictly 2.45 gigahertz waves being emitted at an angle to suffice. Based off the tiles, it is about at a 5-foot distance from one another. I have been able to receive signals and harvest some waves up to 10 feet, but it does compromise the speed of the harvesting. So I decided to, for this presentation, do 5 feet distance. Similar like before, we're using the harvester. It is currently set at 1.2 volt threshold voltage and is selected for the Wi-Fi harvesting. And we are currently using the 50 millifarads capacitor, this one right here. And the output voltage is set to 4.2 volts. I currently have it hooked up to the microcontroller here, which is installed with a voltmeter that records the data for the volt of the capacitor and also the voltage out when the threshold voltage is met. These two is connected to the battery itself. It is set for the low impedance battery, since we are charging a rechargeable portable lithium battery connected to ground. Gets fed to this USB port, and in return goes from USB-A to USB-C to charge the battery bank. Here you see currently the voltmeter is reading off a capacitor voltage of about 1.1 millivolts, 1.1 volts, sorry, and a voltage out of 4.6 millivolts. This is just the static from the device itself, and no actual current is being released as of right now. When this capacitor voltage reaches 1.2, it should trigger the threshold voltage, and the capacitor that has been charged will release all the current into the battery bank.
Okay. Were you guys able to see the video?
Yes.
Yes. Is there any questions or comments?
Yes, I have a question.
Yeah, go ahead.
Yeah, my question is, let's say there's something, an object getting between the signal source and the signal harvester. How it's gonna affect the output, like the output voltage? Yeah.
So similar to how Wi-Fi usually works, if there is more objects in between the source to the actual receiving device, the speed will decrease. So similar to that, if there is more objects in front of it, the harvesting voltage will decrease because the wave will be obstructed. Unfortunately, it's actually more severe than it is from just using it as a Wi-Fi source. So if there is a significant large object in front of it, the harvester will come into problems and not harvest at the speed that you require it. Usually, from what I've saw, it increases about twice the time that it takes for it to without the actual object in front. So this is still like an upcoming technology, and then it's not to the perfection where it should be in a practical sense, but it's just a proof of theory that it could work to charge electronics at a further distance. It could be applied more into a field where direct signals is being sent to that device itself. That would be the best case scenario.
All right. All right. Thank you.
Yep.
Any more questions for Jonathan? Yeah, Jonathan, you did start with 5 gigahertz,
Yes.
5G.
So I did start my first project that I wanted to start with was actually utilizing the new 5G 5 generational cellular towers, since they have a lot higher frequency and smaller wavelengths. So my theory was if I was able to capture those signals, I'd be able to actually like charge the devices a lot faster. But I did run into some problems because the technology is fairly new. So not a lot of places do have that 5G availability around the area. Another problem was that those waves don't travel as far as other waves like radio waves like you get from Wi-Fi and so on. So then another problem I did run into is the cost of actually acquiring a receiving antenna that will be able to capture those five generational waves, which are about 28 gigahertz. So then there is a big cost to that kind of project. I did choose to go lower into the Wi-Fi waves, and then I had to choose between 5G and 2.5 gigahertz and 2.45 gigahertz. And since the 2.45 gigahertz is the most readily available Wi-Fi waves that we use currently in the country or around the world, I chose to choose that wave because it is more commonly used than the 5 gigahertz wave. But in the future, there is a possibility to be able to harvest the 5 generational cellular waves when it becomes more readily available around the world. And it could be technically used to charge a lot faster and a lot more efficient. But that technology has yet to come about.
Yeah, thank you. Did you find out the price or the cost of the 5G antenna if you were to purchase that?
Yes, so the 5G antennas unfortunately aren't sold as individual antennas because they do come from a manufacturer. They only do sell in bulk. So I was able to find a couple antennas, but when I reached out to a manufacturer, they informed me they don't sell individual units. They do only sell large package for corporations that try to integrate 5 generational cellular waves into their building. So unfortunately, that's not something I can purchase by each one unit. Estimates that I've gotten are over $1,000 per antenna.
Yeah. Thank you. So how much did the overall project cost?
It did go over budget, so I did have to end up using some of my money. The harvester board itself cost about almost $400. The other thing, the battery pack cost about $20-$30. The biggest thing that I had to use my money for has been the antennas itself, because I did underestimate the power of the antennas. I started out with a receiving antenna of 4 dBi, which was not enough to even be able to capture any waves. Then I slowly upgraded to a 10 dBi antenna, which ended up working, but I didn't get the distance that I needed. Later on, I upgraded to a 15 dBi antenna, but unfortunately, when I did purchase that antenna, it was a emitting antenna. So when I connected it to the harvester, it did not capture any waves. But when I used it as to be able to emit, it worked perfectly fine. So then I used that to improve the router so it emits a stronger wave. And then I ended up purchasing a 14 dBi antenna, receiving antenna, that actually did work with the harvester itself. So at the end of the project, I ended up having like 6 different antennas that I ended up buying to see which one works the best. So I think at the end ended up being about $600.
Thank you. Any more questions for Jonathan?
I think I do. I pretty much got what you were saying about all this Wi-Fi, and as a matter of fact, I used it. I did. Are you familiar with TeamViewer?
Yes.
I just installed it yesterday to practice remote controlling different devices. I actually used it to like control all my computers. I set up a network between all my computers last week, and I used it to like transfer some of my files back and forth. You can also use it for.
Thank you so much. Could I ask
This
the
is
audience
Dr.
to
Carol. This is
Oh,
Dr.
Dr.
Carol.
Carol, yeah. We're glad you could
Hi.
join us.
I'm
Yeah.
having trouble with Cisco with WebEx, and I'm embarking on problem solving. An observation about the study. First, generally, you should lay out your entire design. And when you're sourcing materials and sourcing products, each product, unless it's a research device, has a range of specifications that it's supposed to work with. And for it to be on the general market, it's supposed to have been tested for that. So while it's a problem not to have been able to find a 5G antenna or to find one that didn't work, at the beginning of a project and when you get to your first job, the engineer you work for is going to want to see the entire layout and going to want to understand why you're buying these products from those vendors and what their performance specifications are. Finally, if you discovered the 5G problem, you could have gone to 4G because there's plenty of 4G devices and networks right now. Your basic idea of trying to do energy harvesting is a good one. But I just want to remind you that when you get to your first job, you have to lay everything out and you'll have to get it approved.
Yeah, thank you so much. Yeah, actually, I did look into the 4G network, but I decided it's probably going to be easier to use Wi-Fi because it's going to be a much direct source that I can actually control itself. With 4G, it all depends on where the antenna for the 4G cellular network is going to be. At least from my area, knowing that I was going to be at home working this project, I don't really get really good 4G coverage around this area, unfortunately. It's mainly woods. So I decided to go more towards the Wi-Fi section of it. But yeah, I really hope to be able to like I said, this technology can definitely be improved a lot more. This is just more of a proof of concept, and I feel like the 5G, the 5 generational cellular network is definitely something that's going to really improve all technologies throughout. And I feel like energy harvesting is one of those things that could definitely benefit from it in the future.
Well, what I want to say about that is for a company to have a 5G license, they've bought a part of the bandwidth or the frequency. So you have the specifications just by virtue of who the carrier is. The second thing I want to say is when you take electricity and electromagnetism, the mathematics for calculating what happens to frequencies under different circumstances is all there. So I think you could have done some math along the way. It's great to have an idea and to try it, and you just go for it. But on the other hand, in industry, it's very expensive if you have a product that's late or one that you've had to redesign and buy more materials for.
Yeah, thank you so much for the advice. I definitely will take that more into consideration. The math definitely, I definitely do agree. I should have done a little bit more math regarding those situations so I can determine which antenna would have been more efficient. I kind of just went with stuff like that. So, yeah.
Again, if you run into older engineer as your first boss, you're going to have to do the math and the design before you're allowed to do anything. And it's going to have to go to a design review with everybody looking at it. So something like what's going on today.
As an alumni.
Absolutely, that is correct. Yeah. That is Dr. Carol from IEEE Washington, D.C. Society. Okay. We're glad you could join us, Dr. Carol.
Oh, I'm always excited by the projects and by the enthusiasm and the chance to help someone out early in their career so that they have a long and successful career. So thank you for inviting me, Dr. Sasanya.
Any more questions for Jonathan? It's our second presenter here right now. We have Jonathan, you can release the screen. stop sharing screen.
Yeah, I believe I stopped. Is it not?
Oh, okay.